So I'll be talking today about practical implications of theoretical deep learning. Okay, so we will start by setting the stage, laying out the case that I will try to make today, and that is that practice needs theory in deep learning. And so deep learning is obviously immensely successful. It transformed a multitude of application domains. It beats the world champion at Go. It is able to converse with humans. You saw a talk by Shai earlier today showing that it can drive cars. And a bit of shameless advertising, an MU bit, we use it to control manufacturing plants. However, this technology has a dark secret, and that is that we don't really understand what's going on. We don't know why these algorithms work the way they do, what makes one model better than the other. This is mainly a heuristic science. It's driven by trial and error, intuition, conventional wisdom. And this leads to various shortcomings. Just to name a few, the models that we develop are oftentimes susceptible to adversarial attacks. They can be fooled in ways that human cannot. They exhibit biases that we do not want. Okay? Here's an example of Obama being completed as a white person. They leak private information. Okay? You can reproduce training examples, which is something that you often don't want. And they're very hard to interpret. We don't really know why they make the decisions that they make. And the argument that I will try to make today is that maybe theory can help alleviate these shortcomings. Okay, so there's a famous quote by Einstein that the most practical solution is a good theory. So I'm not claiming that all the problems will be solved by theory. I am arguing, however, that theory can play an important role. And that's what I will try to convince you today. So we'll start by presenting theoretical deep learning in its basic form, laying out the fundamental questions. Okay, so if you want to formally talk about deep learning, you have to start with statistical machine learning, because at the end of the day, deep learning is a special case. So here is the basic statistical learning framework. We have an instance space X. This is the set of objects that we would like to infer something about. Okay, so for example, if you're classifying 100 by 100 grayscale images, then your instance space could be 100 by 100 matrices. Every entry in the matrix holds the intensity value of the corresponding pixel. Okay? We have a label space Y. This is the set of possible labels that we can assign to instances. So for example, it could be the reals if we are measuring some continuous property, or it could be a finite set if we are classifying. There is some distribution over labeled instances, some distribution that characterizes the world. We do not know this distribution, but we assume that it exists. And finally, the last property of the world is a loss function. This is a function that intakes two labels and returns a non-negative number that indicates the extent to which they deviate from one another. So if the labels are the reals, the label space is the reals, then a reasonable loss function could be the square difference, for example. Our task in statistical machine learning is the following. Given a training set S, okay, which consists of m pairs xi, yi, m labeled instances, we assume that they are drawn IID from the world's distribution. And given this training set, our job is to return a hypothesis, also known as a predictor, that minimizes the population loss. What is the population loss? That is the average loss, the average discrepancy between the true label and the prediction when labeled instances are distributed according to the world. So we would like to return a predictor that minimizes this thing. The problem is that we do not know the world's distribution. So we cannot compute this thing explicitly, let alone minimize it. What we do, if you sweep away a lot of the details, is very, very simple. We fix a hypothesis space, a set of predictors. We fix it in advance. Okay, this could be your neural network architecture, for example. And given the training set, we return the predictor, we return the hypothesis that minimizes the empirical loss. What is the empirical loss? That is the average loss, the average discrepancy between the true label and the prediction. But now the average is taken over the training set. So this is something that we could actually compute. We just run through the training set, compute the average loss. Now, there are three fundamental factors that determine the quality of the final solution that we return. And this is an illustration. Okay, so in the outer box here in gray, you can see the set of all possible functions, all possible predictors. F star D, this is the optimal predictor, the one that attains the minimal population loss. It has nothing to do with us. It's just a property of the world. In H, the blue inner rectangle, that is our hypothesis space. That's what we fixed before seeing the training set. H star D, this is the predictor that's optimal within our hypothesis space. Okay, so it depends on our choice of hypothesis space, has nothing to do with a training set though. H star S, this is the predictor that does the best job on the training set. So this does depend on the training set that was randomized. And theoretically, we should be able to find this. We just run through all predictors in our hypothesis space, compute the empirical loss of each, and return the minimizer. In practice, though, this search is often difficult, hard, even impossible. And what we do is we return H bar, which is some approximation here. It's some approximation. And we care about the population loss of H bar. And it is governed by 3 factors. Number 1, approximation error, also known as expressiveness. This results from the fact that our hypothesis space might not be able to represent the perfect predictor. Okay, so there's a representational penalty that we pay here. The second source of error is called the estimation error, also known as generalization. And intuitively speaking, this results from the fact that the training set is finite. Okay, so if the training set were infinite, then a predictor that does a really good job on the training set would also probably do a good job in the real world. In practice, though, the training set is not infinite, and you might overfit. So there could be a big gap here. And finally, the last source of error is a training error, also referred to as optimization. And this, again, results from the fact that we can't always find H star S. Sometimes we can only return an approximation. Overall, the population loss of H bar is governed by these 3 factors: expressiveness, generalization, optimization. And statistical learning theory in its basic form, as it relates to supervised learning, is all about these 3 factors and how they behave. And they behave in deep learning in ways that are very different from what we're used to seeing in classical machine learning. So let's reflect for a moment about that. So in classical machine learning, we usually choose models and set up problems in a way that the empirical loss minimization, the search for H star S, boils down to a convex program. So we're minimizing some objective that looks like a big bowl. And this is something that we could actually do efficiently. So we could actually find H star S, and that means that there's essentially no training error. It's all about the approximation error and the estimation error. And for these, for expressiveness and generalization, there's the famous bias-variance trade-off, which intuitively speaking means that if I take my hypothesis space and make it larger, the approximation error obviously goes down. I can represent more. But the estimation error will go up. I will be more prone to overfitting. And vice versa. I make my hypothesis space smaller, the approximation error goes up because I can represent less, but the estimation error goes down. I will be less prone to overfitting. So there's a trade-off here. And overall, I think it's safe to say that the theoretical machine learning community has a feeling that we have a fairly reasonable understanding of what's going on here. In deep learning, the situation is very, very different. And it starts off from the fact that the empirical loss minimization is no longer a convex program. So you're minimizing a non-convex problem. And now there's not just one minimizer. There's not just one H star S. There are a lot of them. And a priori, it's not clear that any of them can be efficiently found. But somehow, variants of gradient descent are able to reach one of these. And we don't really know why. And in terms of expressiveness and generalization, approximation error and estimation error, the situation is even more peculiar. And that is that we pretty much know for a fact that some hypotheses with a low training error, some H star S is generalized well, but others don't. And for some reason, on typical problems with typical data, meaning the problems for which deep learning works, gradient descent somehow reaches one of these solutions that do generalize well. And we don't know why. And maybe most surprisingly is the fact that there seems to not be a bias-variance trade-off. Okay, you take your hypothesis space, you make it larger, obviously the approximation error goes down, but it seems that the estimation error goes down as well. So larger models overfit less. And all in all, I think many would agree that we don't have a sufficient understanding of what's going on here. And in its basic form, the theory of deep learning revolves around the supervised case and addresses these questions. And what I am arguing today is that by studying these questions, you could actually gain practical advantages. And I will give two examples of such theories with practical implications. The first example will be a study of expressiveness through tensor analysis. Okay? This is based on a fairly long series of papers, all done at the Hebrew University with my PhD supervisor, Amnon Shashua, and students Or Sharir, Yoav Levin, Ronen Tamari, and David Yakira. Here we are looking only at expressiveness, only at approximation error. Okay? In a nutshell, what we did is we showed an equivalence between convolutional neural networks, CNN, which is the cornerstone of modern deep learning, and hierarchical tensor factorizations, which are high-dimensional generalizations of SVD. We showed that these two things are equivalent. Hierarchical tensor factorizations are very widely used in applied mathematics and quantum physics, and through this bridge, we were able to import tools from these domains and analyze the expressiveness of convolutional neural networks. So we proved various things. I'll just give here two examples. The first one relates to widths of hidden layers in a CNN. So right now, there's no clear principle on how you should set the widths of hidden layers. How many channels should each hidden layer have? Not any rigorous theory behind this. And what we proved is that the width in deep hidden layers, ones that are deeper down the road, that is important for modeling, for expressing correlations between pixels that are far apart in the image. And on the other hand, the width in early layers, that's more important for modeling local correlations. And this means that depending on the kind of correlations you'd like to model, you can design your CNN. You can choose the widths of your hidden layers. For example, if you're classifying large objects, then you care about correlations over distances, and that means you need your deep layers to be wide. On the other hand, if you're only classifying small objects, then it's actually more important that the early layers be wide. And we demonstrate this empirically. This is just a sample from a really simple experiment. We take handwritten digits from MNIST, different sizes, locate them randomly in an image. We try out two networks, one that looks like this, so the early layers are wide, another one that looks like this, the deep layers are wide. The first one is better at classifying small objects. The second is better at classifying large objects in accordance with the theory. So here you get a practical guideline on how you should design your network according to your prior knowledge on a task at hand. Another example relates to pooling geometry. So usually convolution and pooling windows in a CNN are square, but there are other geometries that have also become popular, for example, dilations. And there's no clear principle on when you should use which right now. What we prove is that input elements that are pooled together early, in the earlier layers of the network, they can have stronger correlation. And that means that if you care about local correlations, then using square windows is a good idea. But on the other hand, if you're trying to measure other things like symmetry of an object, then you might be better off pooling together pixels that are reflections of one another in the image. And we demonstrate this empirically. This is a simple synthetic task. You have these blobs, and one prediction problem is to identify how morphologically close they are, so how many little holes, and the other is to identify symmetries. We try out two pooling geometries, one with square windows, one with reflections being pooled together. The first one is better at predicting the local property, and the second's better at predicting symmetry. So again, you get a guideline for designing your CNN based on your knowledge on the kind of correlations you would like to model. Okay? Moving on to the second theory. Here we study optimization and generalization through dynamical analysis. This is based on 4 relatively recent works done at Princeton with Sanjeev Arora and Elad Khazan and students Wei Hu, Yuping Luo, and Noah Golowich. The last paper here is with my student, Noam Razin. Here we look only at estimation error and training error, only at generalization and optimization, and we study specifically linear neural networks. Okay, so linear neural networks, these are neural networks with no nonlinear activation. So the inputs map to the output linearly. but this linear mapping is represented as a sequence of matrix multiplications. So even though you're only expressing linear mappings, and in terms of expressiveness, the model is trivial, in terms of optimization and generalization, it is not. And specifically, you get a highly non-convex problem when you train these models. What we did is carefully study the dynamics of gradient descent over linear neural networks. Carefully characterize the trajectories. Okay? And we were able to prove various things. Again, I'll give two examples. What we showed is that in certain cases, gradient descent over a linear neural network converges much, much faster than gradient descent over a linear model. Okay, so this is just a kind of simple illustration of an experiment that demonstrates this. So in blue, that's the optimization, the loss versus the iteration with a one-layer model. That's a convex problem. In green and red, that's when you add on 2 and 3. That's when you have 2 and 3 layers. So these are non-convex objectives, and you see that the convergence is much, much faster. Okay, this is log scale here, the y-axis. And what this means is that sometimes depth speeds up gradient descent, even though it doesn't give you anything in terms of expressiveness, and despite the fact that it introduces non-convexity. Sometimes non-convexity is a good thing. And this completely goes against the conventional wisdom and the intuition that we have. And I'm showing here the simplest experiment that manifests this phenomenon, but this happens in many, many settings, both linear and nonlinear. And a practical application of this, this is a work by Michal Irani and her group. She talked about this earlier today, is the use of this observation for training a state-of-the-art super resolution system with an internal GAN. They had a very difficult time optimizing a linear generator, and when replacing it with a linear neural network, it gave them much, much faster optimization, and basically this facilitated their system. Moving on to a second example, what we prove is that gradient descent over a linear neural network tends to find solutions with a sparse spectrum. That means that most of the singular values are 0 and some of them are not. That basically means that it tends to find low-rank matrices. So for problems such as matrix completion, this will give you generalization, basically. And we prove this by characterizing the dynamics of singular values through time. So here's a simple experiment. On the left, it's depth 1, middle, it's depth 2, and on the right, it's depth 3. And you see the singular values through time on a matrix completion problem. So for depth 1, all the singular values rise simultaneously. You don't get a low-rank solution. When you have depth 2, then you end up with a small set of singular values that kind of shot up, and you get a large set of, these have large values, and all the rest are close to 0. So it's a much lower rank solution, and indeed the reconstruction here is better. You move on to depth 3, the effect becomes much more potent. You get a number of singular values that are large, and all the rest are basically at 0. Okay? So using a linear neural network gives you an implicit regularization towards low rank. And this, again, was applied in a real system. Okay? This is a work by Jan LeCun and his group at Facebook AI. What they did is employ this idea of using a linear neural network to design an autoencoder that is much, much more efficient and compares favorably against way more elaborate methods like VAEs and things like that. Okay? So this is a second example of how a conclusion born from theory can be used in a real system to gain practical advantages. Okay? So let's now conclude. Start with a recap. I am arguing today that theory in deep learning may help us reach better practice. The fundamental questions in the theory of deep learning are expressiveness, optimization, and generalization. We saw two examples of theories with practical implications. One was a study of expressiveness through tensor analysis. Okay? We derived guidelines for designing a CNN based on your knowledge on the input correlations that you'd like to be able to express. Second example of a theory was optimization and generalization through dynamical analysis, and there we showed that you can obtain faster convergence and an implicit regularization towards low rank by using linear neural networks. And these observations have already been used in state-of-the-art systems, as we saw. And finally, just a word about the road to strong AI. So thus far, the success of deep learning is mostly, I would say, in the context of, in the framework of supervised learning. And there, I think it's clear that heuristic practices brought us much far than theory, okay? On the other hand, there are other settings that are closer to strong AI, like semi-supervised or reinforcement learning, and arguably there we haven't made as much progress. And the heuristic practices, conventional wisdom, the trial and error, haven't gotten us that far. And I am hypothesizing that maybe in order to make significant leaps there and get much closer to strong AI, maybe we also need theoretical breakthroughs. So I encourage every one of the listeners to take part in this quest to make our understanding of deep learning deeper, and hopefully also on the way make it work better. So thank you.
Thank you very much.